sound weird to you because I'm from Israel. And I'm here doing research at UCSB in astronomy, so I'm an astrophysicist. So astrophysicists are, we study stars, the universe, galaxies, planets, stuff like that. And recently, it's really a great time for astronomy now because there's a lot of revolutions happening, and one of them is about gravitational waves. So I'm happy to tell you about that later if you're interested. And I don't know, should we do just questions or general stuff or?
Short presentation and questions?
Okay, yeah. Sure. Yeah, okay, sounds good. So first thing you need to know about astrophysicists, like in most sciences, there are two types. So two types of astrophysicists, and we call them theorists and observers. And in different sciences like chemistry or biology or just regular physics, you have theorists and experimentalists. So basically it's the people who come up with the theories and people who take the measurements and get the data, and you really need these two things together to do science. So I'm an observer, so I use telescopes. We don't actually have a lab that we can do experiments in. We use telescopes. The universe is our lab, so we use telescopes to look at. And one of these pictures is actually fictional. I guess you know which one. Yeah? Okay, before you guess though, I'll tell you actually, it's the one on the right is fictional. Okay, the one on the left is from Interstellar, true, but the equations on the blackboard are actually real. And this is actually a real picture of what theorists do. They work a lot mathematically and write equations, and if you walk into a theorist's office, it will probably look something like that. On the other hand, observers, we don't really look through eyepieces of telescopes. I'm just doing that there for fun. But we actually we connect cameras to telescopes, which are much more sensitive than our eyes. And record stuff that we can then analyze. And it's not a subjective thing of me looking through a telescope and describing to someone what I see. We really get an image. So it's kind of like a digital camera you have on your phone, but it's much more sensitive. So it can see much fainter things. And so actually when you go to really observe at a telescope, a professional telescope, it looks more like this. You're sitting in front of a computer, and the computer is connected to the camera, it's connected to the telescope, and you get your data through there. And even that is starting to become obsolete now, because once you can do it through a computer, you don't actually have to go to the telescope, you can do it remotely. And if you can do it remotely, you can also program the computer to do it by itself. So it's starting to get more and more like robotic, what we call it. So I'll tell you a little bit more about that later. But first, I want to tell you what astrophysicists are not, because a lot of people get this confused. Okay, we are not astronauts, unfortunately. I'd love to go to space. That would be pretty neat. But that's not what we do. You have to remember, astronauts. Right now we have astronauts going out to the International Space Station. It's like a few hundred miles overhead. The stuff we study through telescopes is billions of light years away. Okay? We can only get light from there. There's no way we can ever. Even just going to Mars, which is another solar system, is this huge project that we hope we might be able to do in the next decades. But the stuff we study in astronomy is much, much further away. We have no chance of getting there, so it's totally different kind of thing. The other thing we're not is astrologers. Okay, so please don't get astronomy and astrology confused. Those are two very different things. They started out together, but astrology is basically just fairy tales. Okay, the position of the stars on the day you were born have nothing to do with your personality or what will happen to you next week. It just doesn't make any sense. It doesn't work. Okay, it's just a hoax. Okay, so don't, I sat on a plane one time and told someone I'm an astronomer and said, "Oh, I'm a Pisces." Like, no, don't do that. Okay, no. It's not how it works. Okay, so we actually, we use scientific tools to study the universe, and the main one we have is a telescope. It's what allows us to look at distant objects. And the telescope was invented 500 years ago, and since then, it hasn't, we've essentially been using the same thing, just getting a little bit bigger and bigger. So this is Galileo's telescope, the first telescope, or the first person to point a telescope at the sky. These things are getting a bit bigger. This is a telescope in Mount Wilson outside LA, used by Edwin Hubble, famous astronomer, discovered the universe was expanding in this telescope. So you can see a chair and a desk there at the side, so it gives you a sense of how big this telescope is. And the reason you want a big telescope is it can collect more light. So the more light, it's like a light bucket. Okay, the bigger the bucket, the more light you can collect. The fainter the things you can see, and the further away you can see, And that's pretty neat because light takes time to travel. So if you're looking at the moon, it takes about a second from light to get from the moon to your eye. So you're actually seeing the moon the way it was a second ago, not right now. If you want to know what it is right now, you have to wait a second for light to get there. The sun's a few minutes, light minutes away. Okay, so if you're looking really far, you're seeing things at how they were billions of years ago. And so each telescope is kind of like a time machine, and the bigger it is, the further back in time you can see. Okay, so here's the telescope at Palomar, outside San Diego, which you can actually visit. So the thing there at the bottom is people sitting down there. So this is when they inaugurated the telescope, so you can see how big that is. The size of the mirror there is 200 inches big, and so you can really see far away with that. And these, and there's definitely there's no place to put your eye on a telescope like this. You put a camera and you get the images through the camera. Okay, and they're getting even bigger. So this is the biggest telescope we have today. There's actually 2 of them in Hawaii. So now the little things for scale are cars. Okay, and these 2 huge domes, each of them has a huge telescope whose mirror is about the size of this classroom. Okay, and this thing has to move around the sky and point to wherever you tell it to go. So it's really neat to get to use these telescopes. And building bigger ones. So the Europeans are building a bigger one, and the US with other collaborators are building a bigger one. The University of California is actually one of the big partners. So the one on the top there, okay, you can see the little cars on the bottom. These are simulations because these telescopes don't exist yet, but they're building them. You can see how big they are. The one on the top is a 30-meter diameter, so it's, if you take this classroom like 9 times, that would be about the size of the mirror of this telescope. So this is the name they came up with for this telescope. Since it's a 30-meter telescope, they're calling it the 30-meter telescope. This is how creative astronomers are at naming things. The European one, is a very large telescope, but actually very large telescope is taken already. So they've called it the extremely large telescope. Okay? Yes, this is not very creative in naming telescopes. But these things are going to come online in the next few years. And we don't really know what we're going to see with them because we've never seen this far into the universe before. So it's going to be really exciting. Okay, and here in Santa Barbara, actually, we have the headquarters of an observatory that's very different than these. It's unique. Instead of having one big telescope, okay, that you put at one place, okay, what's the problem with that? You could have bad weather, and then you can't use your telescope. Or things change in the universe, and sometimes they change within hours. And if you have a telescope and you want to observe something now, and it's daytime there now, you have to wait till nighttime, and then you're limited to the length of the night, and as soon as the sun rises, you have to stop. So what this observatory here in Santa Barbara has done is we put smaller telescopes, but we put them all around the world. So this is called the Skumis Observatory. And so, for example, our telescopes are a bit smaller, but they were all built here. So we have 9 of these telescopes that, the mirror's about this big. And we put them all around the world. We have these big, you put them in domes and you ship them out and you put them at these observing sites, which are usually on top of tall mountains. So, you have less atmosphere to look through, and the conditions are dry, and there's less clouds, and, you get really good skies at these places. And then we have these 2-meter telescopes that are even bigger, and we have 2 of those. And we have 1 in Australia and 1 in Hawaii. So, astronomers put their telescopes at really nice places to visit. Hawaii, the Canary Islands, Chile, this place it's fun to go to. But these telescopes, no one has to go to because they're all operated from here, from Santa Barbara. So we have our headquarters not far from the airport in Toledo. And we control all of these telescopes from here. And actually, so, it's not, we're no longer looking through telescopes. And we're not even actually operating them anymore because it's all operated by robots. So these telescopes are all autonomous. Each telescope looks outside, see when the sun's setting. If the weather's good, it opens and it starts observing stuff. And when the weather turns bad or the sun rises, it closes on its own. So we don't have to do anything. And it's all controlled by our big robot here. So these aren't physically robots. These are computers that are doing this. And the robot we have here is the one that decides what each telescope is going to look at. Okay, so how do you do that? We have scientists from all over the world, and they're putting in requests. So I want to observe this thing. I want to observe this thing. I'm studying this star. I'm studying this galaxy. There's about 10,000 requests at any given moment. And this thing has to juggle them and fit them in this kind of 11-dimensional Tetris game and put everything in order and get a plan for what to observe tonight. So it does this. It has about 10,000 requests from 50 different science programs, and it takes it all into consideration, and some are more important and some are less, and it has to know. And some can't be done any other time, and some can. And so it has to take all of that, put it all together, and put it, this is what our schedule looks like. Each line is a telescope, and you can see there's daytime, and then at nighttime you have all of these observing blocks. That is like different stuff to look at the sky for different people. It's constantly looking at things. And then, you know, weather could change, or someone could say, actually, I don't want to do this, I want to do something else. Or something can happen and someone says, oh, I have to observe this urgently now before it goes away. But actually, we plays the status game every 15 minutes and juggles these 10,000 requests. This is the kind of stuff you can do by just writing smart computer software that you can do anywhere else. So I think before we move on to the kind of science we're actually doing, what are the stuff we're looking at that's changing all the time that we need all these telescopes for, maybe we should do some questions.
Sure.
Yeah? Okay.
Do people have questions about like?
So you said that there was revolutions happening. So can you explain like some things that have changed or in like recent years?
Okay. So this itself, having, you know, a network of telescopes, it's not just you have one telescope, you have many, and it's not just individual ones, they're all connected in a network. It's something we couldn't have done before the internet, obviously. But even then, you know, you're constantly talking to these telescopes and getting data from them. So just the fact that the internet is as fast as it is and computers are as fast as they are is something new we can do now. So with this network of telescopes, for example, if a star explodes, what we call a supernova, we can get on it immediately. It doesn't matter if it's daytime here, it's now nighttime in Australia. So we point our telescope in Australia. We can do it immediately. We couldn't have done that before. And then once the night is over, we don't have to stop. Right? If the night is over in Australia, it's now the beginning of the night is in South Africa. So, you know, the other telescope can pick up where the one is starting. So that's one revolution we have now, and we have so much data we're getting from this, and we're kind of overwhelmed, and we don't know how to deal with this. So one thing, for example, is, you know, we're observing hundreds of these supernovas. How do you keep track of that? So one of the things I was tasked with doing when I came here to do some research was, we'll figure out a way how to keep track of 100 supernovae, and like what are we observing and why. And so, you know, I thought, well, we all kind of keep track of a few hundred friends through Facebook, right? So why don't we have a Facebook for supernovae? And that's what we did. I can show you it later. So we actually have this Facebook for supernovae that all the scientists that use our system can log into it and see each supernova as a profile page with all the data, and people can write comments on it. And, you know, request observations and get more pictures, or, you know, stop getting pictures. And so it's kind of like social supernova software we're having is pretty new. But the bigger revolution is like everything we've been doing in astronomy ever has been based on getting light from distant sources. Okay, telescopes collect light, visible light, or maybe infrared light or ultraviolet light, but it's still light. And there are tons of stuff going on in the universe that don't emit light. Black holes, for example, dark matter, stuff we can't see into stars. And so we weren't able to study that. But that changed last year with the first detection of gravitational waves, which is a completely different thing. So gravitational waves allow us to see things that don't emit light. The first thing they detected was actually two black holes merging. That's something we never have seen before, or didn't even know was going on. So it's like, you know, it's like you're at a party, but everything's on mute. You can just see people, and then suddenly someone unmutes it, and now you can hear everything that's going on. This is a kind of revolution of gravitational waves, that we suddenly have this whole new thing. So you can hear things you couldn't see before, and now we want to combine the gravitational waves with the light we get at the telescopes at the same time, so that we can hear and see these things together, and then we'll just learn a bunch of stuff that we didn't know before. It's like just laws of physics that we're not aware of because we were blind to this until recently. So this is all happening now. It's like these years. It's really, like this hasn't happened for 500 years and it happened last year. So, you know, it's a really exciting time in astronomy now. Things are changing really fast.
What type of data are you pulling from the telescopes?
Yeah, so what we get from the telescopes are images.
Okay.
So let me show you. Okay, let me show you an example here for a supernova, for example. Okay, so we have this. Here's, for example, an image from a telescope. So what you see there is a spiral galaxy at the kind of at the edge. It's not actually what we're interested in, but this is an image taken by a telescope. And you know, if you're looking for exploding stars, you take images every night. So here's an image taken the night before, and you basically play a game of like, what's the difference? Anyone see something different about the two pictures? This is what you do all day if you're looking for supernova. Yeah.
There's a star like on the edge
Yep.
that appeared.
Exactly. So okay, so we actually have some software to help us with this. So what you do is you take one image and you subtract it from the other one, and then you know it removes everything that's the same and leaves the thing that changed. So now you can see there's a new point of light that wasn't there the night before. Okay, this is one star in that distant galaxy that exploded. And we caught it right when it happened. So this is the kind of data we get as images, and then what you can measure is how bright that is, and then you take these images in different colors and you can measure what color it has, and that tells you how hot it is. And then you can take this light and split it through a prism, and then you can see what elements are there. So you can see and how fast they're moving. So for like supernova, you can actually measure stuff is moving at 10,000 miles a second, or something like that. So you can actually see that from the light that you gather from these things. So there's a lot you can learn from the light coming from distant objects, but it's still, you know, it's still limited to just the light that they're emitting. Yeah.
How long does it take for the light to reach the telescope?
Yeah, it's a good question. So this thing is, let's see, this is a pretty nearby galaxy, so it's just like something like 25 million light years away. So that's a really long distance, but it's still considered nearby in astronomical scales. But what it means is that it takes like 25 million years to get here. So what I should be saying is the star didn't explode on May 30th, 25 million years ago, and then it did the next day. So, you know, we're watching everything delayed by the distance we're looking at it, but it's still, you know, once it gets here, it's like it's real time. So we actually, you know, scramble to observe these things. Even though it happened tens of millions of years ago, we're just seeing this now, and we want to get on it as soon as possible, because the first few hours of an explosion, you can still kind of see the leftovers of the star, and that's one thing we want to study. So we have this whole system that as soon as one of these things is found, we get like a text message, and it could be in the middle of the night, and we have to run and, you know, point our telescopes at it, even though this happened 25 million years ago. But it's still, you know, we're seeing it in real time as far as we're concerned. So now we're actually having robots find these things, and then instead of sending a text message to us, they'll send it to another robot that will trigger the telescope so we can sleep through the night. And it happens much faster and much more efficiently than if we had to get involved. So,
interruption. If you have to go when the bell rings, you can use the back door. Would be the best way.
very timely notice. Okay.
And if you want to move closer now, this is kind of like, I guess you could say, phase 2 with pizza.
So you guys ready to hear more?
Yes.
Okay, so Alex was asking me earlier, how does one get to be an astrophysicist studying exploding stars and black holes using robot telescopes? And so my answer is completely by accident. In high school, I was kind of focused on, so I majored in math, physics, and computer science. But you know, what I wanted to do was go into physics, like elementary particle physics, the stuff they study at these huge colliders underground in Switzerland, and like colliding particles together to find the basic laws of physics, and like what makes up the tiniest things of matter. And I ended up studying the exact opposite, the biggest things. And that happened because, so when I started, you know, so I went to undergrad and I majored in math and physics, because that's really what you need to do, like elementary particle physics. So I studied math and physics, and then went to grad school and started studying particle physics. But the first year of grad school, we had a professor's strike, and so they couldn't teach us any classes. So instead, they said, well, you should do these labs that typically are done at the end of the first year, after you've already decided what you're going to specialize in. But since we can't do any classes, we'll do the labs sooner. at the beginning of the year. And so one of the labs I did was in astrophysics, and I think I have this letter I wrote to the person who was administrating this saying, well, I never did astrophysics.